Okay, this is the set. The set contains two elements, which is -1 and 1. We want to check that either this set is group or not group under addition and under multiplication. Okay, now first we check under addition, either it is group or not group. Here you can see that when we add these two elements, 1 plus -1, our answer is 0, but 0 does not belong to this set. Then what does it mean by? It means that the first property has failed. If the first property has failed, then it is not group under addition. Now we check under multiplication. Here also you can write the table. How you will draw the table? You will draw the table just like as you will write the element horizontally and vertically. -1 and 1, -1 and 1. It is just like here our operation is addition. Binary operation is addition. So you can see -1, okay, under addition, -1 plus 1, it is -2. Okay, 0. Okay, 1 plus -1, 0, 1 plus 1, 2. So the elements that have generated over here, -2, 0 and 2, these element does not belong to G. These elements are not in G. So you can say that this is not a group. And if I take the case of group table, case of just like multiplication, write the element horizontally and vertically, -1 and 1. Multiply them. -1 multiplied by -1, it is 1. -1 multiplied by 1, it is -1. 1 multiplied by -1, it is -1. 1 multiplied by 1, it is 1. So 1, 1, -1, -1. All these elements are in G. All these elements are in G. Then what does it mean by? Then it means that G is group under multiplication. Okay, so can you say that this is actually the solution of x square is equal to 1? Yes, x square is equal to 1. And if I take x is equal to 1, x is equal to 1, then the table will be just like 1 and 1. Okay, 1 and 1 means the set G is equal to 1 only. So under addition we check that it is 2, but 2 does not belong to this set. That means that under addition it is not group. And if I take the case of multiplication over here, multiplication, then 1 multiplied by 1, our answer is 1, and this 1 belong to. Okay, you can also check the other properties, just like inverse and identity element. Okay, just like over here we check the identity. How you will check the identity? The identity is multiplicative identity. Our multiplicative identity and multiplicative inverse. Remember there, what is multiplicative identity and what is multiplicative inverse? Okay, so in case of just like -1, okay, if I take -1 from here, you can see, is there any element when I multiply -1 with that element, the answer is same? Yes, of course, and that element is 1. Okay, let I take this element. Is there an element exist over here when I multiply this element with that element? Answer is again 1. Yes, it is 1. So the identity of each element exists over here. Okay, so Similarly, we can check the inverse. In group table, just like these are all group tables, if the elements or the elements of the set, after adding and after multiplying, then you can say that that is a group. Okay, so x is equal to 1, x square is equal to 1, and then cube root of unity. The cube root of unity is x cube is equal to 1. Okay, when we solve it, then our elements are just like g is equal to 1 omega and omega square, where cube root of unity, it is just like omega cube is equal to 1. Okay, we draw the group table over here, 1 omega and omega square under multiplication, 1 omega and omega square. Multiply 1 with 1, 1. 1 with omega, omega. 1 with omega square is omega square. Now you can take omega, multiply omega with 1, it is omega, 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 omega square, omega and omega cube, which is equal to 1. Omega square multiplied by 1, it is omega square and omega, omega cube, which is 1. Omega square and omega square is omega 4, which can be written as omega cube and omega, which is 1 dot omega, and it is omega. So all these elements are the element of G. All these elements that are formed in this table are the element of G, which means that cube root of unity is again group under multiplication. Okay, now we check that cube root of unity is abelian group, and abelian group are that group which satisfy the commutative law. So commutative law is over here just like 1 dot omega, 1 dot omega, answer is omega. Okay, and omega dot 1, omega dot 1. When we multiply omega with 1, answer is again omega. Okay, it is omega in two cases. Okay, 1 multiplied by omega, answer is omega. Omega multiplied by 1, answer is omega. In two cases, answer is same. So it means that commutative law is true over here. If the commutative law is hold, then it means that it is not only a group, but it is also an abelian group. Abelian group is that group which satisfies the commutative law. Okay, so we will proceed next. In the next lecture, we will move again forward, cube root of unity to fourth root of unity. In the next lecture, I will discuss about fourth root of unity, and we will also discuss about nth root of unity. Okay, see you in the next lecture.